Good morning, student. Today we are going to see what is the potential energy of a magnet in a uniform magnetic field. So we are going to keep a magnet in a uniform magnetic field, and what is the potential energy possessed by that magnet in that uniform magnetic field. For that, we are going to consider a uniform magnetic field. So uniform magnetic field is represented by parallel magnetic field lines. So this is uniform magnetic field of strength B. In this magnetic field, we are keeping a bar magnet Ns of length 2L. 2L is the length of the magnet. It is kept in the magnetic field. So when it is kept in the magnetic field, it will experience a force in the direction of the magnetic field. On south pole will experience a force opposite to the direction of the magnetic field, and it will come to rest, making an angle theta with the field. So now this magnet experiences a torque due to the magnetic field tau p. The magnitude of the torque is given by magnitude of Pm into magnetic field. That is equal to Pm B sin theta. Last class we have already derived this expression. So a torque experienced by a magnet when it is kept in the magnetic field is Pmb sin theta. Now if I rotate this magnet through a second angle d theta, again we have to apply a torque. So an external torque must be applied to make this magnet or to rotate this magnet through a small angle d theta. So in order to rotate this magnet through a small angle d theta, I have to exert an external torque tau external. So due to this torque, work is done on the magnet. This work done on the magnet is stored as potential energy. So the potential energy possessed by this magnet is given by Ep is equal to external torque into d theta. So this external torque must be equal to the torque due to the magnetic field. Then only that magnet will rotate through an angle d theta. So this constant, when the magnet is rotated with a constant angular velocity, this tells the tau b is equal to tau e or tau external. So substituting this value in this expression, we will have the potential energy. This Ep can also be given by U. So this U is equal to tau external, that is Pm B sin theta into d theta. So total work done. So this is small amount of work done. Our total work done is equal to, when I rotate this magnet from angle theta dash to theta, we will have potential energy is equal to theta dash to theta Pm B sin theta into d theta. That is U is equal to Pmb is taken outside, Pmb into integral theta dash to theta sin theta into d theta, or potential energy U is equal to Pm B minus cos theta between the limits theta dash to theta. So applying the limit, you will have minus Pmb into cos theta minus cos theta dash. That is, potential energy is equal to minus Pmb into cos theta minus cos theta dash. This tells that potential energy is nothing but difference in potential energy of the two positions. If you take theta dash is equal to 90 degree, this term will become 0. So when this term becomes 0, then the potential energy is given by minus Pmb cos theta. So this expression will give the potential energy possessed by a magnet when it is kept in the magnetic field. So when theta is equal to 0 degree, then U is equal to minus Pm into B. Or when theta is equal to 180 degree, potential energy is equal to Pm B. So it can also be represented by cross product or dot product. So this expression tells that magnet will possess minimum potential energy when it is aligned in the direction of the magnetic field. So when the magnet is aligned in the direction of the field, it will possess minimum potential energy. When the magnet is aligned anti-parallel, that is, when the magnet is aligned anti-parallel, then the potential energy of that magnet is maximum. Thus we see that when a magnet is kept in a uniform magnetic field, that magnet will possess potential energy. That potential energy is given by the formula minus Pmb cos theta. It can also be written as dot product. U is equal to minus Pm dot B. Potential energy is minimum when the magnet is aligned in the direction of the magnetic field, and it is maximum when it is aligned anti-parallel to the magnetic field.